right? Last year. Exam. Questions. First try. Huh? No, or shy. Okay. Alright, never mind. So, for this particular one now, which is a sample, I've got some questions from some of your friends to say that, I said go through question 156, but some of the other friends were saying that more about question 2, 3, and 4. As far as you're aware, I think you ought to believe that this course has undergone certain changes since this particular year. So I would say that 2, 3, and 4 are not really relevant. So, ignore 2, 3, and 4. Okay? So this one, we'll go through question 156 because they are still covered in the scope of your course. Okay? Alright? And that's also the other reason why it's still in total. Because if question 156 are also not covered in the scope of course, then we will be putting in total. Alright? Okay, so ready? Because the solutions are provided, so there's also no reason why we'll be spending too much time on it. Okay, question 1, briefly analyze advantages and disadvantages of it. Okay, in the context of systems and cultural engineering. Alright, so this is what you will get if you have read the notes. Okay, so it will say that effect can help on surface projection and robustness and uncertainty and so on and so forth. Alright? Okay, answer is there. Really no need to go into detail. For the benefits, I see a lot of chattering. Not interested. Shall we skip it? Huh? You want to go through this? Oh, because you're giving me feedback that you're not interested, right? So, okay. Alright, so the disadvantages. Disadvantages, I think it's not really what we put here other than measurement noise, but more of like we have high gain, too high a gain, right? You may disregard the system, alright? And you need proper low noise measurement sensors, and etc. Alright? So those are the drawbacks. Okay, B, which will be more relevant. So I wrote here that this question 1 is basic control theory that you have to know. Okay? Will this be tested? So some parts like D, as far as I can remember, D and C, okay, was tested in one or two of the past exams. Alright, so you still have to know the control theory. As I said, this is a very theoretical matter. Okay, it's not all about calculation. Alright? So there's certain things that you have to memorize, especially the first part of the course, right? Okay. So B, advantages and disadvantages of each term in the PIP control scheme. Alright, so you have to know that there are 3 terms, KP, KIOS, and KES. Okay, so KP, alright, to provide an overall gain. Alright, if you have too large a KP and small state error, but the KP margin will be greater. Data calculations. Integral gain is to work on a low frequency response. Okay, that's what we have mentioned in the lecture. Whereas differential gain is on a high frequency response. Okay? And integral gain eliminates the steady state error, so you can bring the steady state error to 0. Alright, there's a problem with integration because you may end up pointing out go into saturation. Okay, and then renders it useless. Right? Okay. C, Why is it highly undesirable to have a low frequency measurement noise in a feedback system? Why? And why high frequency measurement noise is relatively unimportant. Okay, so this relates to your sensitivity functions. Okay, so what is the coefficient that is tied to your measurement noise in output? P, right? Okay, the complementary sensitivity. Alright, so the answer says that okay, the closed-loop transfer function from measurement noise to output is T, which is a complementary sensitivity function. So if we were to draw the graph, T starts from 1, right, at the beginning, and then goes to 0. So under low frequency, okay, if you have measurement noise, the measurement noise is multiplied by 1, right? So it's reflected in the output. Okay, but at high frequencies, your noise is attenuated, so it doesn't reflect on the output. Right? So this is what we say. For low frequency, T is close to 1, and measurement noise will reflect the output. Yeah? Okay, what about crossover? In the crossover region, if you greater than 1, you will amplify measurement noise. Okay, and further emphasize the need for low noise sensitivity. Okay? Alright, this is quite a model question, and this is the model answer. D, which processing elements are added to the feedback loop? When the controller is implemented in digital form, so this is not quite relevant. The portion is more for digital control, okay? Yeah? So I'm not going to go through this, right? Okay, so that's all for question 1. Please don't come and ask me about question 2, 3, and 4. Alright. Okay, question 5. Okay, question 5 is a very typical question that we often say. Okay? Very typical question, right? So, I think you know what it is, you know that long pattern, E and N and Y and R. Okay. By means of a sketch of a typical vector program, indicate the vector margin for the group K and alternative vector margin for the equals K. Okay, and explain how this can be used to characterize relative activity. Alright, because I this diagram, this is what we always draw. Okay? Alright, we ask for loop gain. So you must tell me that this is L, J omega. Right? We ask you to indicate the vector margin. Right? So a lot of these things are extra. So we're asking for the vector margin. So you draw, right now it's -1 and the nearest point. The distance between -1 and nearest point, tell me that's vector margin. Okay? And then inverse loop gain. So you're supposed to draw, which is not here. But in your solution, you're supposed to draw 1 over L. Inverse loop gain, right? Loop gain is L, J omega. Yes? Right? Yes. So inverse loop gain, 1 over L. But we don't draw it here, right? But in the exam, you're supposed to draw. Okay, so don't just see the answer and then memorize the answer and then think that if I'm going to draw this, I get 2 marks. You didn't get half the mark. Okay, because this is not a perfect answer. Okay, you answer according to the question, you don't answer according to the solution. Okay, so this is what I'm going to tell you. The question asks for the inverse loop gain. Alright, so in your notes, what does the inverse loop gain look like? The shape of a fish. Okay, so if you don't know what it looks like, go to your notes. Okay, go to draw a fish. Alright, and the same thing, indicate the alternative vector margin. So this is RM. Alright, for the loop gain, the vector margin is SM. Okay, so next figure is supposed to draw, you draw the inverse, 1 over L, which is shaped like a fish. Okay, and you mark from -1 to that 1 over L, and then mark RM. Is that clear? Yes? Alright, and then explain how this can be used to characterize relative stability of the closure. Alright, sometimes, depending on the question, so this solution is not perfect. Because this solution is not answering the question. But it's quite obvious without me telling you that this solution is not answering the question. Right? The question didn't ask you for gain margin, it didn't ask you for place margin. It didn't ask you for the definition of place gain margins. Okay, so this solution is not answering the question. Alright, please don't just memorize the solution. Okay, that's straightforward. But then, of course, this solution is, if the question has asked you to draw a Nyquist diagram illustrating the gain, the stability margins. Okay, and then provide the definition of the stability margins and how they can be used to characterize close to stability. Then this is the solution. Alright? Okay? So what are you supposed to answer for this is how that can be used to characterize relative stability of closed loop for the vector margin, because they always ask you about vector margin, right? So when you write this part, right? Vector margin. Okay, you say the more informative measure is the vector margin SM, which is the distance from -1 to the closest point to L naught. Okay, and you say that the inverse vector margin RM, okay, is the distance from the point -1 to the closest point on top of 1 over L naught. Alright, so that's the answer to this question. Okay, move on, part D. Explain why picking the sensitivity function S0 and complementary sensitivity function T0 should be avoided by performing the following analysis. Many of you, the minute you read this sentence, you jump into explaining why S and T is important and why you want to start picking and blah and blah and blah. But is that the question? Huh? Is that the question? The answer is no. This is not the question. Okay? Explain why picking in S0 and T0 should be avoided. It's not the question. You're just supposed to read that. It's just a guidance. Okay? So what you need to do is by performing the following analysis, so the question is in part 1, 2, 3. Because these are the sections that are awarded marks. Yeah? There's no mark here. Understand this? Okay, so this is English, how you read English. There's no mark here. So you have to answer this. You answer part 1, 2, and 3 because there are marks there. Understand? This has been tested before, and then students are answering why you want to avoid picking in T and S and why it is important and try to draw all the graphs. But you're not asking for that, right? Okay? So there are no marks here. Nothing. Alright? So you should go to part 1. Whereby you have 4 marks. Okay? So this is where there are marks. Is that clear? Yeah, okay. Because I don't want to go through the motion of like, why did you do this and that? Why? Waste of ink. Part 1, derive the closed loop equation of the system. Okay, so basically, you write down what is y equals to how much is r, how much is t, and how much is n, right? This. Okay? Very important equation. Alright, so you will probably should memorize it. And discuss how picking will affect the system's response to R, D, and N as defined in question of Okay, so first thing, you write down this equation. Okay? Alright? And tell me that this is T, this is F, this is T, so write down this again. And then we'll discuss how picking will affect the response. So if you are picking in T, alright, that's increased noise and reference response. Picking in S will increase the total sensitivity. Okay, and then you get 1 marks. Alright, easy to see marks are awarded 1, 2, 3, 4. Alright? Part 2 shows that the vector margin for the inverse looking is equal to the inverse, the peak value of P naught. So basically, show that Rm, okay, Rm is equal to 1 over max of T, which we have gone through in the lecture. So if you have taken down notes, you can show that. Okay, that's your problem. Okay. Symmetry argument is usually described the effect of S on the vector margin for the loop A. Okay, so symmetry argument, okay, describe that Sm is 1 over max of Sm, right? So that's what you can do. Okay, so in the lecture we did say that this defines Sm. Alright, Sm, the vector margin, is the distance from -1 to the nearest point of L naught. Alright? So, distance from -1 to the nearest point of L naught is this, magnitude 1 plus L naught. Okay? J omega s. Omega s is the distance, the point, the frequency point at the nearest point. Okay, so you can write this. Alright, this is 1 plus Cp. Alright? L naught is Cp. And S naught is 1 over 1 plus Cp. Correct? Right? So 1 plus Cp will be 1 over S naught. You got that? Okay? S naught is 1 over 1 plus Cp naught. Okay? And the definition of Sm is 1 plus Cp naught. Okay? So this is 1 over S naught. Got that? Alright? And because Sm is the minimum distance, the shortest distance, the closest distance. Okay? So if you want minimum of Sm, your denominator will be maximum. Alright? So this 1 over max for the particular frequency. Okay? Alright, then you move on to Rm. Rm is the distance between -1 to the inverse loop gain. Okay, the closest distance between -1 to the inverse 1 over L naught. Alright, so this magnitude defines distance. Okay? And then if you work it out, it's 1 plus L naught over L naught. Alright, and the definition of P naught Cp naught over 1 plus Cp naught. Okay, so you can see easily that this is the reciprocal of P naught. So this is 1 over P naught. Right? So Rm is 1 over magnitude of P naught. Okay, similarly, Rm is the closest distance from -1 to 1 over L naught. Okay, so closest meaning minimum. So how do you get minimum of Rm? You get the minimum of Rm from the maximum of the denominator, right? Okay, so Rm is 1 over max magnitude of P. Alright? Okay? And that's all. 6 marks. Easier. Easy? Okay. Part 3. This is what show that T naught is equal to the sensitivity of S naught to changes in the plant T naught. And the symmetry argument briefly describes the effect of S naught on the sensitivity of T naught, right? So we have roughly gone through this in the lecture as well, and in the tutorial. So basically we are saying saying that, you know, if there are changes, alright, if there are changes in the fund P naught, okay, how does that affect S naught? Okay, meaning delta S naught over delta P naught equals to T naught. Just tell me that. Okay, that's the question. Show that delta S naught over delta P naught is T naught, which is something that we have done. Okay, so basically, just write down this, which is over here. Right? This one. Okay, so sensitivity of S naught to plant variation. Okay, so sensitivity of S naught to plant variation. Okay, so if you read this, the solution is inverse. The solution is inverse to this question. Alright, so the first part of the question says show that T naught is equal to sensitivity of S naught to changes of plant. The answer is here at the bottom. Okay, so this answer is answering the first part of the question. This is answering the second part of the question. Alright, so don't just memorize the solution. Okay, so what I'm supposed to write for me is here for the first part of the question. Right? So you want to investigate sensitivity of S naught to plant variation. So what you do is delta S naught over delta P naught. Okay, and then how do you get this? You're supposed to do delta S naught over S naught, right? And then delta P naught over P naught. Alright, so this is delta S naught over delta P naught times P naught over S naught. Okay? Yes? Right? Yeah? Okay, and then if you do this, you work out with this. We have gone through in the lecture and the tutorial, so I'm not going to go through it again. Okay, and show me that this is minus CP naught over 1 plus CP naught. Okay, you tell me that it's minus CP naught. Okay, if those of you, you write this. You write this. And then you immediately equal to minus T naught. Do you deserve any marks? No. No. Okay, answer is no. Alright, you only get 1 mark if you write down this one. Okay? But if you write down that this is equals to minus T naught, then you don't get any marks at the bottom. Alright? You understand? You must tell me that this is minus CP naught over 1 plus CP naught. Because effectively, if you differentiate, you get everything in C and P. You don't get things in T. Yes? Okay, so you must show me the intermediate steps that goes to here and then it equals to minus T naught. If you immediately write down this equal to minus T naught, I'm sorry. Okay? Alright. Then this part of the solution that says in the frequency ranges where T naught is small, which means you have a small gain, S naught is relatively insensitive to variations in the plant. This is, you write this if you ask for it, but in this question you didn't really ask for it. But if you write this, then it completes the solution. Okay, so our question will be explain, like, what does it mean, right, in terms of sensitivity analysis. Okay, so if this is minus T naught, then when T naught is small, S naught is relatively, in the region, in the frequency range where T naught is small, S naught is relatively insensitive to variations in the plant. Okay, because delta S over delta P naught is small. Alright, so changes in the plant doesn't affect S naught. Okay, you got that? The next part of the question by the symmetry argument describe the effect of S naught on the sensitivity of T naught. So the answer is on top. Yeah? So instead of doing you do delta T naught over T naught over delta P naught over P naught. Okay? Then you go with delta T naught over delta P naught times P naught over P naught. Alright? Okay, and then you show me that this is 1 over 1 plus CP naught, which is equal to S naught. Alright, and this says that in frequency ranges when S naught is small, Alright, T naught is relatively insensitive to variations of the plant. Okay? So don't just memorize the solution, because that's not answering the question. Okay, alright. 5 plus 6, 11 plus 4, 15 plus 5, 15. Okay, 20 marks. Can you score 4 marks? You should have. Okay? Otherwise, it's difficult to get A. You don't score 4 marks, at least for my section. Okay, we move on to question 6.
跟周一的差不多，对不对？周一的你要 balance 上，你要他的 score 好，周一的 score 差不多的，又靠哪了？周一的可以放。
Okay. Assume that the nominal plant P naught changes to some other value. Okay? So there's been change in the plant. Basically, you change the loop gain from L naught to L. Alright? If this change causes a Nyquist plot of the loop gain L naught to move L, which is closer to the -1 point, explain how this may affect the closed loop sensitivity function S and T, and how this in turn may adversely affect the various performance targets. Okay, so basically it's telling you that L has changed to L. Okay, so how does that affect S and T? So we tell you that when L has changed to L, your minimum distance to -1 from L is called vector margin. Okay, and the minimum distance from 1 over L to -1 is the complementary vector margin, so there's SM and RM. Okay, so if your L naught has changed to L, alright, SM and RM will be reduced. Okay, and because SM is 1 over max of S naught, and RM is 1 over max of T naught. Okay, so peak values of S and T are the inverse of SM and RM. Okay, so peaking, alright, peaking will then be increased under this perturbation because if SM and RM are reduced when L naught has changed to L, okay, SM and RM are reduced. Still start to see a lot of blur faces now. So SM is 1 over max of S naught. Okay. And RM is 1 over max of E naught. Okay? So this question says that L naught has changed to L. Okay? And because SM is 1 over max of E, okay? L naught changed to L, SM reduced, RM reduced. Yeah? Okay? SM reduced, RM reduced, SM is 1 over max of this, RM is 1 over max of this. So that's peaking. Because this is lower, so this is bigger, right? This is lower, this is bigger, right? So it tells you that S naught and T naught increase. Yes? So that's peaking. Okay? Alright, so there's amplification in disturbance and measurement noise. Make sense? Straightforward, it's just one line like that. But of course, this is not what you write for the solution. This write in full complete sentences. Okay? But you can write me the equation and explain why. Okay? 4 marks.
一定会给你分吧，不是4 marks。
Understand? Yeah. B. Derive conditions in terms of loop gain and inverse loop gain perturbations, which characterize the robustness of the closed loop stability when the plant changes from T naught to P. Derive conditions. So sometimes we may ask you to say derive conditions. in terms of loop gain and inverse loop gain perturbation, meaning, okay, when L naught has changed to L, and when 1 over L naught has changed to 1 over L. Alright, so the question says, when L naught has changed to L, and when 1 over L naught has changed to 1 over L. Means there's a perturbation in the loop gain and the inverse loop gain. Derive conditions that characterize robustness. Okay? So derive conditions that characterize robustness. In your lecture, what did you derive that characterize robustness? Robustness analysis. There's only one here criterion, right? The Doyle's stability criterion. Okay? So when you read the question, obviously you don't understand the question, but you need to try to understand it. Okay, so what the question is asking for is loop gain and inverse loop gain perturbations. Meaning is if L has changed to L and 1 over L has changed to 1 over L, derive conditions for robustness. Okay, I'm sure many of you when you read the question you don't understand it, but if you look at this, you understand it. Yes? I hope you understand it. Okay? So robustness condition, there's only one criterion that you have learned in the whole of this course. That's called Doyle's stability criterion. Okay? Alright, so part B is asking for Doyle's stability criterion. So all you need to do is write down the entire criterion. And that's 6 marks. Okay? Sometimes we will ask, we will say derive conditions, we will say derive necessary and sufficient conditions. Okay, same thing. Still the Doyle's stability criterion. Okay, as long as you see that we mention, okay, loop gain and inverse loop gain perturbation, derive necessary and sufficient conditions. Okay, and you see that we mentioned robustness when the plant changes from P naught to P, give us the Doyle's stability criterion. Is that clear? Yes? Okay? Because I realized that there's a difference between Glasgow students and Singaporean students in terms of reading the question. Okay, and our students typically have a lot of difficulty in trying to read and understand the question. I mean, sorry lah, no offense, but this is what we see. Okay, so that's why I'm trying to explain to you that when you read the question, don't get scared off by the question. Chances are you already know the solution, but you're not so clear about what they're asking for. Okay, so, alright? Okay, so what is Doyle's stability criterion? Alright, so just answer the question. If there's a perturbation from L naught to L by Doyle's stability criterion, okay, L minus L naught over L naught must be less than or equals to, okay, you wouldn't write W1 immediately. Right? Correct enough. Okay? You're right that this is CP minus CP naught over CP naught. Okay? And then you work out that this is CP over CP naught and then minus 1. Then you work out that this is related to P1 over P naught, right? Okay? And then you say that this has to be less than or equals to P must be less than or equals to 1 over P1. You just follow electrons. Okay? So that's Doyle's stability criterion. And then you work out the same for the inverse. Okay? 1 over L minus 1 over L over 1. Alright? Any questions over here? Okay, so there's, as I said, this is a very theoretical module. Alright? There are 3 parts of this module. The first is sensitivity functions and how they relate to stability margins. Okay? The second part of this module is on PID controllers and the what? Pole placement. Okay, for polynomials. The third part of this module is on state space and also co-placement, right, with state space. Okay, so for the first and second part, it's already very theoretical with a little bit of calculation. So for the first part, when you see a question like this, like question 5 and question 6, there's not memorization, you have to memorize. Okay, but you only know what to memorize because we've been telling you over and over again, especially in the tutorial and this part, for example, that these are the basic things that you have to memorize. Okay, alright? Let's move on, part C. Closed loop system with normal plug and not. Okay, a base margin of 20 degrees and frequency of 5 hertz. And again, margin of 3 dB was the time of failure. So when we go through this in the tutorial, yes? It's in the tutorial. Alright, so what we are asking for, which is actually not the question. Here. Okay, so that's not a question. The question is this. Part 1. By how much can the plant gain increase before the closed loop becomes unstable? So we tell you that the gain margin is 3 dB. Okay, so how much can the plant gain increase before it becomes unstable? Let's convert 3 dB to the raw value. Okay? So dB means 20 log of x. Alright? So 20 log of x is 3 dB. Okay? So you calculate what is x. X is 1.41. Okay, so for those of you who have Garcia or Sharp, make sure you get this. Okay? So answer is the gain can increase by 1.41 before the closed loop becomes unstable. Alright? You get 1.41, those who are pressing the calculator. Yes? You get 1.41? I don't know what's the name. I think yeah, if you get 1.41? Yes? Okay, now B, part 2. Additional delay can be added to the closed loop because the duty is lost. Hey, just a disclaimer. Just a disclaimer. If you have any questions, please make sure you ask now. Because once I finish my lecture, don't come back to me and say, ma'am, I have a question on this. I'm not going to entertain you. Okay? So if you have a question, you ask now. Alright? So part 2, what additional delay can be added to the closed loop because the duty is lost? We tell you that the phase margin is 80 degrees and the frequency of 5 hertz. Okay, so what you do is convert 80 degrees and 5 hertz to time in seconds. Alright, so 80 degrees over 360, which is 1 revolution, times the time period. Okay, so time period is 1 over 5 hertz. Alright, so 80 over 360 times 1 over 5. 0.044. So maximum delay that can be added before the closed loop becomes unstable is 0.044 seconds. Okay, and that's 20 marks. So can you get 4 marks on this? Yes. Alright. Okay. So this is all that we're going to cover for this. Alright. Let's take a 10 minutes break so we'll come back and talk. So for those of you, before I say my disclaimer statement, if you have a question on this,